Okay, so to understand the phosphorus cycle, we have to first start with the rock cycle. And we have to look at what we're talking about when we're talking about the rock cycle. Something you've covered in middle school, I'm sure you remember. You have magma. You can start anywhere in a circle, right? So magma, molten rock in the right underneath the Earth's surface, can be pushed up. And as it's pushed up, it starts to cool and turns into rock. So this semi-liquid kind of fluid rock material starts to cool off and turns solid as it comes up. It comes up in what forms? It comes up in as through volcanoes, through cracks in the Earth's crust. It could hit water to finally cool. You've seen volcanoes, you've seen lava. When magma crosses the Earth's surface, we call it lava. This can also push rock upward. As it cools, hardened rock, even if it cools here near the surface, even if it doesn't come out in a volcano and just cools underneath the Earth's surface, it can be pushed up. And you have mountain creations like in the Himalayas or the Rocky Mountains. All that is rock that's been pushed up as magma underneath might bubble up and push upwards from the deeper core of the Earth. As the uplift continues, you have outcrops, mountains, small mountains, large mountains, continental divides. As weather happens, cooling, rain, sleet, the rain turns into ice and cracks start to form in the rock, start to break up into smaller rocks. You have landslides. These movements, this weathering, this constant erosion of the land starts to break it apart and starts to move it physically. The rain can also react chemically with the rock, changing it. And finally, you get sedimentation. That rock can flow down a landslide into a creek or a riverbed. It can be pushed down into pebbles. That all can be finally settled there in the riverbed, or it can be pushed further down to the mouth of the river, like in the Mississippi. Or it could, if the particles are small enough, they might be, and they're weathered in the right way, they can become ionic and be soluble in water and be carried out into the ocean. In any case, ultimately, all that rock that settles down and becomes solid settles at the bottom of the ocean, and that sediment can get buried. As burial happens and rock tectonic plates shift, that rock can be formed into metamorphic rock or can melt completely and turn into magma. So metamorphic rock is things like limestone turning into marble. But that doesn't have to be the end of it. It could also go right into magma and become part of some mineral composition that turns into some form of igneous rock. So igneous rock are things like granite. Or the metamorphic rock might be uplifted itself. So you get large deposits, large mountain ranges that have marble in, that people can cut out, like in Italy, the famous Italian marble. Or it might be, again, melted into magma and reconstituted into some other form of rock that we call igneous. Igneous rock is rock that's settled and allowed to cool slowly over time, and so you get large crystals in the rock. The crystals form only if they're allowed to sit for a very long time and cool slowly. The metamorphic rock are not completely melted. They're pushed and pulled and heated, and so they deform. They form waves in the rock. That's why when you see marble, you see wavy lines in the rock itself, no matter what the color is. And the color of rock all depends on the minerals that were in it when it formed. So you could have iron in the rock and it might be a little red, or you might have copper in the rock, it might be a little green. or fluorine in the rock, and you might have a little purple or a little some combination of that. So you can have all kinds of colors. So that's the rock cycle, and it's constant. Minerals and rocks are constantly being buried and upheaved and melted and remelted and changed metamorphically and spit out in volcanoes or just pushed up and made into mountain ranges. Now, I say constantly, but it's also a geologic time. So even though it's constantly happening, it's happening over millions and millions and hundreds of millions of years. Not anything that we can really watch, except maybe a volcano erupting. We could watch that, or we can see the land cooling on the Hawaiian off of Hawaiian Island as the lava hits the water, the ocean, and forms new land. Those are fast ways of seeing parts of this cycle, but we didn't see the millions of years it took for that lava to move from the magma chambers beneath and get slowly pushed up as pressure continuously increases over time. What we see are the moments in that geologic history. That's the rock cycle in a nutshell. There's some details you should know, and of course we'll talk again about tectonic plates, but let's go on and look at phosphate and what happens to phosphate in general. And so you see here, there's the uplifting, the mountain ranges that are pushed up from underneath. How do we form mountain ranges? Tectonic plates meet and push the land upwards. This land was magma. It was a fluid form of semi-liquid rock underneath the Earth's crust that slowly cooled and then pushed up as the tectonic plates smashed against each other. And I say smash, when you and I think of smash, we think of a glass breaking on the ground. When tectonic plates crash, they crash over millennia. And they push and push and push, and as they push, land moves. But the land is at such a large scale. I mean, we're talking about building mountains, we're talking about continents hitting each other. That there's such a large scale that the movement is inches a year. So the rock uplifts, and as things weather, and in this rock there's phosphate. Remember, phosphate is phosphorus with oxygen. Now, phosphate comes in many different forms, and you can have many different minerals attached to phosphate. And so it forms all kinds of minerals. But phosphate, in essence, is 4 oxygens attached to a phosphorus atom. So this phosphate is in rock, and it's trapped in this mineral that's very difficult to get out. It's in a rock. It's part of a rock. So I don't know how long it would take you to break a rock apart. But even if you broke it up into dust, it still would be trapped with other elements in a crystal. And so the weathering of the rocks is the first start. The rocks start to weather, the water, the rain, the air, the wind blows on it, breaks it apart, but also changes it. Also starts to chemically change the phosphate trapped in the mineral, and starts to prepare it to be released into a form that can be soluble in water. So the phosphate, the weather weathers the rock and releases the phosphates. It's in the soil, it's in the water, but then it's very difficult even then for the plants to take it up. So much of the phosphate runs off into the ocean and then finally sinks down to the bottom, solidifies as it goes into sedimentation, becomes part of the rock, and enters the rock cycle again. So even though there's phosphate here, not a lot of it gets incorporated into living systems. And so it takes a whole slew of things to occur for that uptake. So let's take a look at some notes here. I got this out of a paper, a research paper, about how phosphate is taken out of the taken out of the rock. And what you notice is that first, one of the first things that's difficult for plants to do is how do you get the phosphate out of the rock? So one thing is you need a low pH, an acidic environment in order for the phosphate to be released, for it to be released in a way that plants can use it. And some of that acidic environment can be created by animals or even plants producing CO2 and releasing acid, right? Carbonic acid or organic acids by bacteria, or things getting, dead things being digested by bacteria. So decomposers release organic matter, the phosphate and organic matter, and then root hairs, the plant root hairs, which we've seen before with the nodules in the nitrogen cycle, the nodules formed by bacteria can help bring nitrogen into the roots, or fix nitrogen for the plant. But here we're talking the root hairs can take and that phosphorus that's been dissolved by the acids that are created when decomposers degrade or eat organic matter. They are doing respiration, and so they're producing CO2. They're producing carbonic acid. They're producing other types of acids that then help dissolve the phosphorus. That dissolved phosphorus then is released in a soluble form so that the root hairs can absorb it, can assimilate it. Apatites are the form of phosphate where you have phosphate, here's a P with a circle around it, is bonded to several minerals, and they form basically a cube, and so that the acids help release the phosphate from this cube, this matrix, this crystal, allowing the phosphate to be absorbed into the roots or the rootlets of the cell, the plant. So the minerals and phosphate can be attached to carbon, it can be attached to fluorine, it can be attached to a lot of different elements. All of those are known as apatites, minerals in the rock that trap phosphate. And the phosphate's released, and it's by these acids, by these organic acids produced during the eating of organic material. The second is the plant roots themselves can dissolve them by releasing organic acids. They can again dissolve those bonds between phosphate, that's phosphorus with 4 oxygens, right, and some other atoms or other minerals. And then finally, once you get the phosphorus in a place where it could be absorbed, the phosphate is not very mobile in the soil. If you think of nitrate is very soluble and moves with the water. Phosphate's soluble, but only when it's in phosphate form. It's quickly bonded again to form other insoluble minerals. And so there's this slow rate of diffusion so it takes a long time for the phosphate to get into the rootlets, into the roots, into the plants. And again, we need that phosphate into the plant. So much of the available phosphorus is in the organic matter that the bacteria are degrading, that the decomposers release. So that degrading material, that those dead bunnies, dead animals, dead plants, dead or organic matter sitting there has phosphate trapped, just like the phosphate was trapped in the rock. So in order to release that phosphate, the plants have to have an enzyme to do that. So plants have these soil microbes, these bacteria, as we've discussed before. They have developed this phosphatase. It's an enzyme that releases the phosphate into an inorganic form of phosphorus. Inorganic, right? So this phosphate, for instance, from the organic matter. It separates it from DNA, from RNA, from ATP, from GTP. It releases those phosphates into an inorganic form. So you get this phosphate instead of DNA, right? Or RNA or whatever other organic molecule it's involved in. And by doing that, the plant can then absorb the phosphate and use it to make its own DNA and RNA and ATP and whatever else it needs to make. So the second way that they've done this is they not only just have a symbiotic relationship with bacteria, they also form a symbiotic relationship with a fungi. The fungi is mycorrhizae, but it doesn't matter. The name of the bacteria isn't the point. The point is it has a close relationship with this fungus that coats it. The fungus coats it almost like athlete's foot on a person's foot, except the rootlets of the plant are coated by this fungus that then releases this phosphatase that takes that organic material, the dead leaves, the dead bunny, the dead whatever, releases the phosphate, and it also releases organic acids that helps release the phosphate from rocks, right, from minerals that as the phosphate was trapped in. And then that allows the plants to suck up or to take up through diffusion into its roots inorganic phosphate that it can use for biological purposes. So this relationship between this fungus, oh, and by the way, the fungus then gets sugar, right? So the plant produces sugar for the fungus, and the fungus produces the organic acids and the phosphatase for the plant. And together, they form this really close symbiotic relationship. Again, remember, it's called mutualism, right? Where they both get something out of it. So there's a lot of steps to this, and that's because this phosphorus in the rock is not very easy to get to release. Now, if we take a look at where the sources of phosphate might be. So again, normally phosphorus is not found in the atmosphere. Now, there is some phosphorus that deposits from the atmosphere in the sense that it is as a volcano erupts, it sends debris into the air, dust in the air. That dust has phosphorus in it. So in a sense, there is some deposition that could happen naturally from the atmosphere. Obviously, fertilizer, because remember, there's, I guess I could tell you a story. Early on in the use of fertilizer, the British tried to, they found out that the rock that they were digging from a local hill or mountain had phosphorus, and they put it on their crops. And initially, that the crops did better because it had phosphorus in it, and phosphorus was necessary for plant growth, and they knew that. But after a few years, the plants stopped working. They stopped growing. And the reason was that there were other minerals in that rock. It wasn't just phosphorus. There were other minerals in that rock that when released, caused the buildup of salts that were not conducive to plant growth. Things like uranium and cadmium and etc. So finally, the process was perfected where they took and purified phosphorus, nitrogen, and potassium. The three the three limiting agents for plant growth there in that particular soil. So this again became the chemical fertilizer, the process we'll talk about later. That actually you'll need to know the name of it. The process of chemically producing phosphorus, nitrogen, potassium, and just adding that instead of adding rock, ground up rock to the soil, allowed for what's called the green revolution, allowed us to grow enough food to feed the world. So this fertilizer, these chemical fertilizers, are very useful, except that the fertilizer, as you know, phosphorus, nitrogen, potassium, when it rains, it runs off the soil. Either runs off the surface as surface runoff, or it percolates through the soil and gets in the groundwater and comes out. And either way, it comes into the stream. If it's not taken up by the plant, if it's not used up by the plant as it rains, or the water, it ends up in the stream, and then that stream ends up. And here's an example of leaching as you get the phosphorus and nitrogen just leaching out of the soil, being just like the coffee grinds as you make coffee, and out into the stream it goes, finally out of the groundwater into the stream. So this phosphorus in the water ends up in the ocean, and again that ocean, where they're in the primary productivity of the ocean, is also a limiting. Phosphorus is a limiting agent there as well. So ultimately, it's the cycle, to simplify everything, turns out to be the phosphorus is trapped in the rock. We'll start at the solid phase of the rock, up in the mountains that have been uplifted by geologic events. As the weather happens, as rain falls and sleet and ice, the rock breaks up into smaller and smaller pieces. The chemical weathering, the acid in the rain, the various elements in the rain react with the rock and change the form of the phosphate and make it slightly more soluble until it's in the ground as an apatite. So as a mineral that is not in itself able to be readily absorbed into the plant. But then fungi and bacteria, just like in the nitrogen cycle, fungi and bacteria help take that phosphate out of the mineral and allow it to be absorbed by the roots. Also, phosphatase is able to take detritus, dead things, right? Detrivores in the soil. Detrivores are organisms that help digest or break down detritus. Detritus is dead things, either animals or plants. And these detrivores start to break down using phosphatase, or rather the bacteria and the fungi in the soil help take this detritus and allow it to be the phosphate to be released and allow plants to absorb it and make all the different compounds it needs to make. All the nucleic acids, remember nucleic acids have a sugar phosphate backbone, so there's a lot of phosphates in DNA and RNA. ATP, all the different TPs, the ATP, GTP, CTP, all of them are used in biological systems or need that phosphate as a essential component. But most of the phosphate gets trapped in rocks. Eventually, it settles down to the bottom, becomes a rock, as a sedimentary rock. As it precipitates, as it's finally run off over time, that rock is pushed up over millennia, pushed up, made into mountains again. Some of it, if it explodes out through a volcano, some of it might come down as rain and precipitate onto the ground again. But most of the phosphate is involved in this cycle where plants try to capture as much of it as it can, but eventually over time you're going to lose a lot of it. You need to have that weathering of the rock, bringing more phosphate down. An interesting point is that a lot of this happens in some of the best places where these soils, where this kind of weathering occurs, where this kind of release of phosphate and nutrients occurs, is a place called floodplain. So remember, we've talked about this idea that flooding is natural and it helps produce good soil. So if you have the Mississippi River, good old Miss, the Mississippi River often flooded. So where you had, if the banks of the river normally were here, then this is the normal level of the river. Occasionally you had a 5-year flood, or every 10 years you had a 10-year flood, and you had the 100-year floods. And what would happen is the banks of the river would go further up and just flood the land around it. Now that sounds like a bad thing, especially if you have houses in a city nearby. But it's a natural thing. It's a good thing for the land, because as this water that has all these minerals that are broken down from rock and all the mud that it brings from further upstream from the Great Ohio Valley or the Idaho or from Indiana, and all that mud starts flowing down the Mississippi, and it swells up, the banks swell up and deposits all that mud, all those minerals there in the soil. And the bacteria, the fungi, the various detrivores, they're able to take all those dead things that are trapped in the water as the water recedes and the water goes back to what it was at the end of the flood. What's left here is all that mud. And that mud is extremely important. That mud, what that mud does is it produces soil. And obviously soil is necessary for growth. You can't, if it wasn't for this mud that's left over, you couldn't grow your crops, because this is where on the banks, that's why the banks of the Mississippi are so famous for being able to grow so many different crops. So this constant flooding and receding has laid out wonderfully rich soil on each side of the Mississippi. What kind of richness is it? It's nitrogen, phosphorus, and potassium, and many, many other, and of course more organic material, just sitting there waiting to be used by whatever plant, whatever plant someone decides to plant, or whatever tree decides to grow. You can have all kinds of things growing on the side of the Mississippi because of all that soil that's taken so long to build. It takes over 1,000 years to make an inch of soil. But the Mississippi, along the banks of the Mississippi, you have the advantage of having all that soil being brought to you, and thousands of years worth of effort, erosion, uplift, millions of years of uplift, erosion, weathering, dead things dying, being broken down, thick layers of soil being brought down and deposited and laid inch after inch next to the banks of the Mississippi. So that's what makes building dams that much worse, because when the good thing about building a dam is you don't get flooding. And so that's good for someone who lives along the banks of a river, obviously, or at least I think it's obvious, because if you build a dam, and what's a dam for? A dam is so as the river comes down, as you come down the river, if there's a big rainfall, you're able to trap that water behind the dam. I put the dam in the opposite direction. You're able to trap the water behind a dam. The land here is made into a giant lake, which is not very good for growing, obviously. You have a water supply, though. Water that can provide water for irrigation, water that can provide water for cities. So that's good. You can make electricity with the dam. That's good. You reduce unpredictable flood or surprise flooding because you're holding back the water. This is a very high dam, so you're able to hold a lot of water there. But the negative is that the lack of flooding then creates a need for nutrient further south, further away from the dam. So you're holding back all this water. When it rains a lot, you hold the level of the water is high, but the dam holds it back. This water is less than you would expect. There's no flooding, so there's no new soil coming in from up north. All the soil's layering in here and are dredged up. Maybe somebody ships it over, digs it up and is smart enough to use it as fertilizer or sells it as bags of soil. But in any case, the point is that lack of flooding interrupts the natural progression and building up of soil for growth of plants along the Mississippi, along any river. Anytime you do this, you're disrupting the natural process of soil building and nutrient recuperation. So you start to see weathering, the leaching, the normal leaching, and the runoff from the soils along the sides of the river. The phosphate, the nitrogen, the potassium all goes into the river and down into the ocean, but there's nothing coming back and replacing it, or at least not as much, because you're not having the flooding that would normally happen. So you have all the whatever nutrients are in here, but the nutrients along the side of the bank are not being deposited, so you don't get the soil deposition, and therefore you don't get the soil is not able to recoup its ability to grow plants. So what do farmers do? Farmers have to come and add nitrogen synthetically. So you have to add nitrogen. You have to come in and you have to add nitrogen, phosphorus, and potassium by the truckloads to grow your crops. So in any case, the phosphorus cycle is very, very similar to the nitrogen cycle. The big difference between the nitrogen cycle and the phosphorus cycle, both are very, very limiting. They're both incredibly important nutrients that are limiting terrestrial and aquatic net productivity. And the reason that it's limiting that net productivity is that without nitrogen and phosphorus, you can't grow plants. Nitrogen and phosphorus are essential. It's difficult to get the phosphorus. That's going to be a key point. Phosphorus on terrestrial ecosystems and in aquatic ecosystems are very difficult for it to be released from the mineral. It takes a long time for phosphorus to be uplifted, to be weathered, to be broken down, eroded and weathered and dissolved and taken by creeks and rivers to the land through flooding and what have you. And it takes even more time for that phosphorus that's trapped in minerals to be released in an inorganic form, to be able to be absorbed by plants. Even in dead things, it's difficult for dead things, the phosphorus to be released from its chemical bonds to the organic forms that cannot be absorbed by plants. So fungi and bacteria have to further break that down using an enzyme called phosphatase to break that phosphate off the organic molecule and release it in a way that plants can absorb it. And finally, when we build things like dams, we disrupt that cycle because we're not able, the phosphorus is not able to get on the land where it would do the most good. And so we have to add fertilizer, and then adding fertilizer, as you know, it starts to impact the ecosystem by creating eutrophication. You get algal blooms. You get, just in Florida, just this weekend, there was a red algae bloom. And red algae is a type of dinoflagellate, which produces a toxin. It's toxic to animals and plants, and so it's killing sea turtles and other aquatic organisms. And of course, people can't swim in it either. So you have a whole coast in Florida being in. This is a natural phenomenon. Red tide, or they call it red algae or red tide, and all it is dinoflagellates that need phosphate and nitrogen. But whenever we dump it with our fertilizer and it runs off into the creeks, it gives the dinoflagellates the nitrogen and the phosphate they need. So we get these red tides or red algae. They come more often, and they cause this damage and this death as is going on in Florida. All right. Well, I hope this helps, and we'll go over it in class before you complete your FRQ. All right. Bye.